Hello, this is Dr. Joe, and I would like to welcome you to your Bio 101 classroom, outside the classroom, I guess. And today we are going to be talking about how science is conducted. Because if you are taking a course in the sciences, it is really helpful to understand how this information actually comes about. Now, understanding what science is and how we develop scientific information can be a bit perplexing for folks who are not scientists. But let's see if we can come up with a relatively simple definition using primarily examples from biology. And so as we go through this unit, we'll be talking about this and bringing up various examples from biology. For a lot of folks, science is just the memorization of scientific facts that are taught in a class or a classroom. But, that's about the furthest thing from science that I can actually think of. Science is basically trying to understand why things happen. So a physicist is interested in finding out maybe what makes the universe tick. There are different kinds of physicists that study, a lot of different things. An astrophysicist may study the stars and planets, and they might be interested in how the stars and planets are born and what causes them to behave the way they do. So they're interested in finding out something. A chemist may be interested in developing a new chemical or learning why a chemical behaves the way it does. And biologists are interested in trying to determine why the living world works the way it does. Now, even though all these scientists I've mentioned study different things, they do have many different aspects of their jobs in common. And one of these is the way they use something called the scientific method to try to understand the thing that they're interested in. So let's start out by looking at, what we're going to think of is as the classic scientific method. Think of the scientific method as a procedure for understanding something that's unknown. Now, this may seem simple on the surface. For instance, you may want to know why a deer is eating your mom's prized petunias, or why it rubs its head on a tree. Another example is, you've probably always heard that, you shouldn't go outside when it's cold because it'll cause you to get a cold. Is this true? Does more expensive coffee really taste better than cheaper coffee? And if it does, why would the price of coffee reflect anything about its taste? And believe it or not, you can actually use the scientific method to answer all of these different questions. So the first thing we typically do as a scientist is we have made some sort of observation, and we thought to ourselves, why is that working? What's happening there? And we become curious and we want to know what's going on. And really that is kind of a unifying aspect or a key aspect of a scientist is they've got to be curious. And so they see something, and rather than just blowing it off and just accepting it on the surface, they take a closer look. So let's take this common cold example, for instance. You've probably heard that if you go outside in crappy weather, you're going to catch a cold. Now, once you get a cold, there are a wide range of home remedies such as vitamin C, echinacea, zinc, that at least supposedly will help you get rid of a cold. At least, that's what we're told by our moms, our friends in the drugstore, and maybe even a lot of advertisement. But do any of these things really work to help get rid of a cold? Well, I've had a lot of experience with colds, and I really think that vitamin C is the best thing around for a cold, because I always take vitamin C when I get sick, and I drink extra orange juice, and I get better or I get well quicker than all the other people around me who I see with colds, and maybe their cold lingers for 2 or 3 days, and mine is gone within a day and a half. And I know it's because I take this vitamin C. Now, on the surface, this seems like it may be a relatively simple question. Okay? But in reality, there could be a lot of intertwined reasons as to why I get better and it faster, and it takes other people longer to get over their cold. But what I have done is I have made a hypothesis about my observations. Okay, so my hypothesis is that vitamin C is going to help you get rid of a cold quicker than not taking vitamin C. Now, the difference between someone who is a scientist and folks who are not is that a lot of people would then stop with that observation and just assume that they are correct. Okay? But in general, a scientist, once they've made an observation, they don't necessarily assume that they are right. They just know that they've made an observation, and maybe they can develop a hypothesis from it. And the next step is to try to figure out what's going on, or whether or not that, if that hypothesis can be tested. But, I'm getting a little bit ahead of myself. In general, a hypothesis in relation to scientific investigation is a proposed explanation for some sort of observation. Based on things that I've read and my observations on the internet and the information on the vitamin C bottle, vitamin C is helpful to get rid of a cold. So my hypothesis is that if I take the recommended dose of vitamin C, the typical cold would not last as long as if you did not take vitamin C. Now, one of the primary aspects of the scientific method is that the hypothesis has to be testable. So there has to be a way of actually testing it. Okay? And when we say that something has to be testable, we mean that it has to be measurable. Okay, so whatever test you're going to run on it, you have to be able to take some sort of measurement. We have to be able to put a ruler to something. We have to weigh something. Or in the case of our cold and the effect of vitamin C, our measure might be time. So the length of time that a cold lasts with vitamin C, or when you're taking vitamin C, and the length of time that a cold will last if you are not taking vitamin C. And we can be very creative about what we measure, but whatever you're doing, if you are using the scientific method, it has to be measurable. Now, something else is that a scientific hypothesis must also be falsifiable. So you've got to, it has to have the opportunity to be shown as being false. So again, thinking back on our cold example, if I am wrong and you take vitamin C, it would not affect the length of the cold. Therefore, my hypothesis is wrong. It's false. Okay? But that's kind of a critical aspect of it. If you make a hypothesis about something and it cannot be proven false, then it cannot be tested under the scientific method. Okay? Or at least the classic scientific method. There may be other ways of testing it, but it won't be testable under the classic scientific method because it has to be, you have to be able to prove it false. Okay? Now, statements that are value judgments are not scientific because different people will have different opinions. Okay, so it can't necessarily be proven false. One person will believe it's true and one person will believe that it's false, but it's something that can't really be shown to be actually being false. Okay, but in our example, we will be measuring the length of time that a cold lasts. So if our hypothesis was that vitamin C can make you feel less miserable? Well, this is not as straightforward as how long a cold actually lasts, because how do you objectively measure whether or not you are miserable? And you may be tougher than me, and vitamin C does not make you feel less miserable, but we can actually measure the length of time that a cold will affect both you and me and somebody else and maybe 100 other people we're going to test this out on. But if we were to use a measurement like making you feel less miserable or making you feel more tired, that won't work, because that is going to be the opinion of somebody. But something like how long a cold lasts, or especially if we use our measure as being when your fever returns to normal, which on average is going to be 98.6. So we may say the length of time that it takes your body to return to a temperature of 98.8. And that's just to account for, some folks who might normally have a little bit higher body temperature. But once it reaches that point, and maybe let's say, that it's the length of time from when your body goes past 98.8, stays up in the upper range, and then returns to 98.8. That length of time and that objective criteria is something we can actually measure, and it is completely objective, and there's nothing subjective about it. So that is something that can be tested using kind of this classic scientific method. So again, the important part of this is that it has to be in some way measurable. You have to have something that you can actually put some sort of measurement to, and that it is objective. Okay? So we've been going for a few minutes here. This, I believe, is as good a time as any to stop and take a break. And when we come back, we will continue on with our discussion.